is struggling hard on difficult surfaces. Here comes the use of the latest rover technology developed by Spacebit, a legged rover named Asagumo. These rovers can move individual legs to specific spots and can also tilt their bodies. Let's understand this latest space rover technology, and we will also see how these rovers recover after a fall. Before moving further, let's first examine how these rovers perform on an inclined surface. As you can see, both are moving forward with stability. If the angle of inclination is increased a bit, the wheeled rover will topple, while the legged rover will remain stable. Do you know why this happened? To answer this question, we should understand the concept of a support polygon in a rover. Let's draw a polygon using points of contact with the ground. This polygon is known as a support polygon. If the self-weight projection of the rover is within the support polygon, it means the rover is stable. Otherwise, the rover is unstable. When we increase the surface slope, the projection of the center of gravity begins to move backside. And after a certain angle, it lies outside the polygon. As a result, the rover becomes highly unstable and topples over. Now let's see how this high inclination problem is solved using a four-legged rover. The support polygon of the legged rover is formed by the legs in contact with the ground. An interesting thing here is that the support polygon becomes a triangle when the leg is lifted. Now, let's slowly increase the surface slope. When the projection point is outside the support polygon, the rover also becomes unstable. However, this rover can tilt its body by increasing the length of its back legs. Due to this, the projection point falls inside the support polygon again. This kind of operation is not possible with a wheeled rover. This rover is stable now. However, we can improve stability even further by understanding a concept called stability margin. Consider these two cases. They are the same rovers, but with different leg movements. The stability margin is defined with respect to the direction of movement. Just by observing these visuals, you can easily understand what a stability margin is. A higher stability margin is always preferred since it is more likely to remain stable if an unexpected force or high momentum is applied. Now, let's get into the most interesting part of this video, the movement of the four-legged rover on a plane surface. Before understanding the movement of the whole rover, we should first understand the details of the leg movement. In order to move a leg, it should be lifted, extended, and then brought forward. This is accomplished with two servo motors. Firstly, motor 2 is rotated in an anti-clockwise direction, which causes the leg to be raised off the ground. Afterwards, motor 1 is rotated in the anti-clockwise direction to extend the leg. Lastly, motor 2 is turned clockwise to place the leg on the ground. It is clear here that the contact point of this leg has moved forward. In this condition, if the rover body also moves forward, we are done with the rover's forward motion. Let's see how the rover body can be moved forward like this. It is clear that to achieve this forward motion, we need to move all these 4 points of the rover body in a straight line. Before proceeding further, we should clearly understand how these yellow points are affected by the rotation of the two motors. Let's focus on the first yellow point. Let's rotate motor 1 only. When the motor 1 rotates, the bottom limb rotates clockwise and the other limb rotates anti-clockwise. This is due to the reaction torque of the rotor against the stator. Now let's follow the yellow point and draw a path. Now let's rotate only motor 2 and find out the path traced by the yellow point. The trick of the rover body's forward movement is that you mix the movement of these two motors. We can operate motor 1 for a small movement, then motor 2 for another small movement. The net movement of the yellow point is interesting. It has moved forward. However, if you observe carefully, the yellow point has moved at an angle, not straight. To fix this issue, we need to introduce one more motor in the rover. This motor can turn the rover's body or leg in a vertical axis. So the solution is simple. Just activate the third motor after the second motor. The yellow point movement is perfectly straight now. Please observe the beautiful forward motion created by the combined motion of three motors. It is brilliant, right? The same operation is happening at the other three legs as well, simultaneously, to make all the four yellow points move forward. The smoothness of this straight line depends on the minimum angle at which the motors can be rotated. If you remember, we had stopped the robotic movement after the first leg was put forward. Now, with this body forward movement, the rover has reached this position. After moving the first leg and the body, the next leg it should move will depend on maximum stability. Moving leg 3 will provide the maximum stability margin. After that, we move leg 2 and leg 4 to get a complete walking cycle. Now, let's see how the rover turns as shown. The first leg is raised during a turn, and instead of placing it forward, it is rotated using motor 3 first, and then placed on the side. When we repeat the same operation on the other legs, the rover turns. Besides moving forward and taking turns, the rover can also move backwards. It can also move sideways like a crab. Also, it can raise and lower as well as tilt its body. In the course of motion on the moon, the rover takes help from many sensors. HD multispectral camera and LiDAR are the primary navigation sensors used to scan the environment. Apart from collecting data from these sensors, the rover also needs to detect its leg disturbances accurately to react in time and avoid tripping. The sensors used by the rover for locomotion are the inertial measurement unit, touch sensors on feet, encoders, and torque sensors. The touch sensors can tell whether the rover is in contact with the ground or not. The amount of force applied by the ground on the sensors can be estimated using the joint torque sensors. The position of each joint can be given by the encoders. These sensors work together to move the rover forward. Spacebit designed this rover to explore lunar lava tubes on the moon. Since there will be no human presence, the rover must also be able to recover if it somehow flips back on its head. Here you can see the motion of the rover, as well as the rotation and direction of the motors used to get the rover back on its feet. Although this rover is useful on challenging terrain, it has some disadvantages, like the complex design and control system, as well as the slow walking speed, which makes it highly inefficient on flat surfaces.